All right, guys, welcome back. This is one of my favorite sections of the research methods course. And in this one, we're going to be talking all about everybody's favorite subject, statistics. Man, that's a lot of cheers I hear out there. All right, so quantitative data analysis, right? This is where we take all our numbers, we take all our information, and we do something with it. We've spent all this time gathering samples and making research questions and conceptualizing and defining and printing surveys and getting all these surveys back and putting all our information into one giant data set. Okay, now what? We've got all this data recorded in some computer file somewhere. Now what do we do with it? Well, there's two different types of statistics. And this is going to be a relatively short section just because a statistics course is much different than a research methods course. This is just a really kind of bare bones intro to statistics. If you're interested in this or you need to know this, you definitely want to take an actual statistics course. So with that out of the way, the two different kinds of statistics are descriptive and inferential. Descriptive, as the name might suggest, is just describing your data. We've gathered all this data. Here's what that data looks like, right? Inferential statistics is where we're actually comparing two variables. We've got an X and a Y or more, right? We might have 3 or 5 or 20 variables. But we want to know how one affects the other. That's inferential statistics. How do these different variables affect each other? Not just what does each variable look like, but does this variable correlate or modify or seem to track with this other variable, right? And when we're doing inferential statistics, we always need to do some kind of test of statistical significance. We need to have some kind of mathematical analysis that is honestly way above my pay grade. I do not have a degree in math. That can tell us whether this observed motion in X and this observed motion in Y are actually related, or are they just due to completely random chance, right? So these tests of statistical significance, somebody decided hundreds of years ago probably that the way statistical significance was going to work was at the 95% level. In other words, how confident are we that this seeming relationship in X and the seeming relationship with X to Y, how confident are we that that's not due to just pure random chance? What are the odds that we would see what we're seeing in our data set if any relation between X and Y was completely nonsense and it was only due to pure random chance? If we are 95% or more sure that we would not see what we're seeing if it was just due to pure random chance, then we say that is statistically significant. If there's less than a 95% chance that this observed correlation or relationship is due to or is not due to pure random chance, we say it's not statistically significant. So we have to be really, really, really sure that we're not seeing these numbers just based on pure roll of the dice chance before we're willing to say, oh yes, there is a statistically significant relationship between these 2 or 3 or 5 or 20 variables, okay? Now we're going to start with a talk all about descriptive statistics. And again, this is just taking usually a single variable at a time and expressing what that data looks like, what those numbers that we gathered for that variable actually look like. And the most common way to do this, probably, I have no actual data to back this up, but I'm betting the most common way to do this is measures of central tendency. Or in other words, that's a fancy way of saying average. Okay? And there are lots of different ways to calculate an average depending on what kind of data you're using. So you might want to go back and rewatch that section where we talked about nominal, ordinal, interval, and ratio level data, because that's going to come into play here on this slide, okay? So one way to calculate an average is using the mean. And a lot of people use the word average to mean mean, when really any one of these measures of central tendency is equally valid to be called an average. Okay? So if you want to be specific to mean, use the word mean. If it's kind of doesn't really matter and which one of these three you used and you're just using everyday conversation, use the word average. But don't say, oh, that's the median, not the average, because the median is the average. The mode is the average. But the mean is where you add up all the values and divide by the number of values, right? So the average of 5 different numbers, we add all 5 up, then we divide that total by 5. If we have 7 numbers, we add all 7 numbers and divide by 7. And that is our mean, okay? But unfortunately, we can only really use that with interval and ratio level data, right? The median is different than the mean. The median is where we use, we take all of our values. So if we have 5 different values, we're going to take all 5 of those and we're going to arrange them in order. The smallest number on one end, the largest number on the other, and increasing in size as we go across, right? Then the median is just the one in the middle, right? That third value. If we have 5 values, the third one, when we put them in order, is our median, okay? If we have an even number of values, let's say we have 4 values, we put them in order. Now, which one of these two is in the middle? Well, we just take the midpoint between the two, right? So if it's some number and then 4 and 8 and some higher number than 8, we just take the middle number between 4 and 8, which would be 6, right? So the median is either the middle number or the halfway point between the two middle numbers if there is an even number of numbers, right? And with a median, we can also really only realistically use that in interval and ratio level data. But it's a much better, more accurate, more realistic measure of central tendency in the cases where you have lots of really large outliers, right? So the most common place I see the median being used is when talking about like average income, right? So when we talk about, say, in the United States, what is the average income in the United States? Instead of using the mean, we use the median. Specifically because there's a whole bunch of us clustered around the, $30,000 to $130,000 a year kind of range. But then there's a few of us that make billions of dollars a year. And if we use the mean, those billionaires, those extreme outliers would kind of give us an ultimate mean that is not really reflective of what we're really looking for when we say the average salary in the United States. So the median can kind of tamp down the effects of those extreme outliers. So if you have some kind of data where the vast majority of people cluster around a nice normal curve, but then there's a few people at one end of the curve or the other that are just really extreme values, you might want to use the median rather than the mean when describing your average. But again, both the mean and the median can only really be used with interval and ratio level data. For nominal and ordinal level data, the only real choice you have for an average or a measure of central tendency is the mode. And that's the value that appears the most often, right? So if we want to say, what is the average hair color among a group of 1,000 people? Well, the mean and the median, obviously it makes no sense to use those for what the average hair color is, because again, you can't do math with nominal or ordinal level data, right? So when we say average, we just mean the one that appears the most. So maybe it's brown hair. So brown hair would be the average hair color among this big group of people. And we're saying that not because it's the mean or the median, but because it's the mode. It is the value that appears the most often. Okay? Now, another thing we can do with descriptive statistics is variability. So in other words, we've got this set of data. Let's say it's, height. We've got, again, another group of 1,000 people. We want to know what their heights are. And we find that the mean is 5'10", right? But how much variation is there around that? Are there a lot of people that are like 5'9" to 5'11", and then only a few people outside that range? Or there are a ton of people who are like 5'4", 5'5", and then a bunch of people over here who are 6'3", 6'4"? Well, we need to know what that kind of curve looks like. So I have here an image, and you'll notice that the yellow line there, they all take that normal curve shape. But they have very different kind of widths, right? The yellow line is much skinnier. That normal curve is much more centered around our mean of 200 in this case, according to that picture. Whereas the blue line also has a mean of 200, and it's still essentially a normal curve shape, but it's much flatter, much wider, right? So there's lots more of those outlier values that just happen to be clustered around that exact same mean that we had with the yellow line, where there are very few extreme values out on either end, right? So we want to know how much variability there is in our data. The simplest way to do this is the range. And that's just the difference between our maximum value and our minimum value, right? So if we take a quick look at this graph and kind of, just guesstimate based on eyeballing it, it looks like for the yellow line, our sample C for this image, the minimum value looks like it's about 150. The maximum value looks like it's about 250. So we might report this as we have a mean of 200 with a range of 100. Because again, we take the maximum value, subtract the minimum value, we're left with a range or a distance between the minimum point and the maximum point of 100. Okay? Whereas with the green line, it seems like the minimum value is, 75? The maximum value is 275. So if we reported the green line data, it might be we have a mean of 200 minutes, but a range of 200. Right? But that doesn't really give us that much more information. So we might look at the interquartile range. And the way an interquartile range works is instead of reporting the range for the entire set of data, we break our data into 4 quarters. Right? There's the bottom 25%, the middle 25% but slightly lower, the middle 25% but slightly higher, and then the top 25%, right? So now we have all 4 of these quartiles, and we report the range for each one of those, right? So now we can see a little bit better how skinny or how wide that data is. The even more accurate way to do it is with the variance or the standard deviation. And I'm not going to go into the difference between the two. Again, that is much more suited to an actual statistics course. But essentially, that is just a slightly more direct measure of how skinny or wide that curve is. The short version is you cut the data in half at the mean, and then calculate the mean for each half. And that, if it's got a very different mean for that half than the actual mean for the whole set, if that's very different, you have a very wide data set. If that's very close to the actual mean, that is a very skinny curve. Okay? And then finally, there's skewness. And these 3 lines in the sample above all are not skewed at all, meaning they don't kind of lean one way or the other. They are exactly proportional around the mean, at least, if we eyeball it. Skewness is when you have a curve, but each half, right, if you cut it in half at the mean, each half is not equally skinny or wide. And the easiest, most common one for criminal justice majors that I know to talk, to illustrate this concept is the age crime curve, right? So the median age for criminals might be, say, 20 years old. But the shape of the curve before 20 and the shape of the curve after 20 are very different, right? So we would say that that curve, instead of being nice and symmetrical, leans over towards the younger ages, right? So it's a very steep rise and then a very slow fall off, right? That is skewed to the left. Maybe, there's some other data set you can think of that's skewed to the right, where the higher values are much more likely, right? And then it kind of slowly rises and then very quickly drops off, right? So that lean, how that normal curve kind of tends to be shuffled towards one end or the other, is all about skew or skewness, all right? Now, when we're displaying descriptive statistics, there are lots of different options that we can choose from, right? Lots of pretty graphs have been made about all kinds of different subjects, and we get to go through a few. And there's lots of different kind of graph types you can use to display different kinds of data. And which one is best for your situation really is sometimes it's a matter of personal preference. Sometimes it's, fairly obvious, but there are lots of different ways of displaying this kind of one variable descriptive kinds of data, right? So the first is a bar chart, where we just have an x-axis at the bottom and a y-axis on the side, and we mark some thing down on the x-axis, some value on the y-axis, and then we have a series of bars going up so we can see how each of those different values corresponds to each of these different values. A histogram is the exact same thing as a bar chart. The only difference is that in a histogram, the bars are touching. Whereas on a bar chart, they're separate columns. In a histogram, they actually touch each other. That's the only difference. But there is a difference between a bar chart and a histogram, okay? A line graph is where, again, we just have that x and y. We draw points along and then connect those dots with a line. And then finally, there's the pie chart. And the pie chart, with an example here on the screen, is just a circle. And then you kind of divide that circle into different chunks, or usually different colors of different slices, different size slices of that pie. And these are almost always used to show data for percentages, right? So in this example here, we have what percentage of all naps were too short in orange, what percentage of all naps were not long enough in purple, and which percentage of all naps couldn't be completed because the person fell asleep in green. And their relative sizes are shown by their relative sizes in that pie chart. So let's go over a few more of these. Here's a pie chart on the what an average engineer spends their working day doing. So each one of these slices represents a relative size or relative percentage of time, where the whole circle is their entire day, and then say that the purple one in the upper right, that's the percentage or chunk of their entire day that they spend sipping coffee, right? And then there's general Facebooking, specific Facebooking, instant messaging, and that little kind of orangish one near the top, that is the percentage of time they spend working very, very hard. I'm allowed to joke because I know a lot of engineers. Here's a pie chart showing the percentage of the time of when your professor will assign a project, right? So in the green slice, which is, we can tell just from looking at it, is roughly a quarter of the time. The professor will assign a project a month in advance, so you'll forget about it till the night before it's due. The giant red section over there on the left is the same time as three of my other professors. The orange slice is right before finals, and then that tiny little blue slice is when I actually have time to do it. So again, the entire circle is 100% of the time, and then each section is a proportion of that 100% of the time, right? So here's the most simplistic pie chart ever. In the orange, you see the percentage of the pie that has not been eaten. And in the gray, you see the percentage or chunk or proportion of the pie that has been eaten, right? Now, there's a special kind of pie chart. Some people say it's not related to pie charts at all. I am of the opinion that, dang it, they are absolutely related to pie charts, called Venn diagrams. And this is where you have multiple different pie charts, each pie chart representing some category. Each circle here represents some category of thing, and then where they overlap are the things that are found or exist in both groups described by the circle. So in the blue circle, we have cheap, and in the kind of orange-red circle, we have convenient. And so what category of food falls into both of those categories, both cheap and convenient? Well, that's fast food, right? Then the green circle is easy on your stomach, and the blue circle is cheap. But if it's both easy on your stomach and cheap, the only thing that exists where those two overlap, the only thing that exists in both of those groups, both cheap and easy on your stomach, is food that takes way too long, right? But where all three overlap, cheap and convenient and easy on your stomach, the one thing that exists in all three categories is ramen noodles. And I ate a lot of ramen noodles in college. So here's one more Venn diagram, right? So we've got three circles here again. We've got invades homes in one circle. We've got emerges at night in one circle. And we've got immortal in one circle, right? So where immortal and emerges at night, but not invades homes, is vampires. Because vampires are immortal. They only come out at night, but they're not allowed in your home unless you invite them in, right? So they're in those top two groups, but not in that third one. So immortal and invades homes, but doesn't care whether it's night or day. So in the two groups of immortal and invades homes, but not in the group of only emerges at night, are zombies, right? And then where all three overlap, the one thing that is immortal and it emerges at night and it invades homes, obviously Santa Claus, right? So that's how Venn diagrams work. Here's bar graphs. And as you can see on bar graphs, we have the x-axis at the bottom, the y-axis on the side, although this one isn't actually labeled on the y-axis because it's a joke about being bad at statistics. And then each one of the kind of entries on the x-axis has a bar rising up to illustrate the corresponding number or value for that y-axis, right? So here's a bar chart, and this one happens to be turned on its side, so the x-axis is over here and the y-axis is down here. And this is about speed of cars in traffic, right? So in my lane, their average speed is very small. In the lane next to me, it's a lot faster than it is in my lane. And in the lane that's the farthest away from me, it's the fastest. Right? So that's a bar chart. And then here's one more bar chart, all about the number of bar chart related deaths, with obviously the largest one being in green because there's about to be a value of 6 bar chart related deaths as soon as that green one keeps falling over, right? Now this is a histogram. As I said before, it looks just like a bar chart, but with this one, the bars are touching. So as you can see here, this looks a lot like a bar chart, but there's no gap between the bars, between the entries for that x-axis, each bar just kind of runs directly next to all of the others. So here's a histogram I actually found kind of interesting, and this is the length of Greek tragedies in number of words. So somebody compiled all of the, the major Greek tragedy, I guess, plays or books or media, right? And then so along the x-axis, we have their length in words. And then along the y-axis, we have the number that was found, right? So between 4,000 and 5,000 words, there were only 2. But between 7,000 and 8,000, there were what looks like 9 or 10, right? The y-axis doesn't actually go up high enough. But between, say, 9,000 and 10,000, we can tell based on this histogram that there were 5, right? So this gives you a good idea of how long each of those Greek tragedies actually was and how commonly different lengths appear, all right? So here's a line graph. This one is all about my blood pressure when it comes to spelling errors, right? Or grammatical errors. So when I see on somebody's paper an obvious spelling error, my blood pressure rises to 150. If they use the wrong your, goes up to 200. Use of the wrong it's, either with the apostrophe or without the apostrophe, goes up even further. But so we took the x-axis, we took the y-axis, we put dots at each one of the proper positions, and then we connected it with a line, right? One of the most important line graphs you'll ever see is this one. This is from the online comic XKCD. And this is an actual scientific thing that this comic writer has decided to make an extremely simple, very easy to understand line graph all about. So on this one, we have, on the x-axis, we have knowledge of a topic, like actual knowledge of a topic. And then on the left, we have the willingness to opine on that topic, willingness to talk about it and take a stance and argue in favor of your position, right? And theoretically, the line should go straight from, kind of the where the two axes meet and up. But as you can see, it's not a straight line. There's a big hump over there towards the beginning where your knowledge of that topic is actually really low, but your willingness to spout off about it is relatively really high. That is called, in this comic, Mount Stupid. In reality, we call this the Dunning-Kruger effect. And here's an actual set of data showing the exact same information, making the same point, but with real-world data, right? So with this line graph, we have 3 different lines, okay? Now along the x-axis, we have the bottom quartile, second quartile, third quartile, and top quartile for knowledge on a topic or information known about some topic. And I have no idea what the actual topic was in this case. And then on the left, we have the percentile for success, right? So when you ask people, like, how much do you know about this certain topic? You'll see from the solid black line that what people know about a topic what people think they know, their perceived ability, doesn't really vary much with their actual ability, right? That white line is their actual test score. The one going, I guess this direction perfectly, from kind of the lower left all the way up to the top right in almost a straight line. Those are actual test scores, right? So the perceived ability and perceived test scores, if people kind of realized what they know about a topic, should follow that, right? That exact same pattern, but it doesn't. Because people who know the least about some subject think they know as much as people who, actually know about a subject. That's called the Dunning-Kruger effect. You can read all about it in another course or, Google it. It's a fascinating topic. One more thing we're going to talk about is scatterplots. And scatterplots, it's, kind of sort of similar to, say, a line graph, but without any lines, right? So you got your x-axis, you got your y-axis, and then you put dots for every value of whatever you're talking about, right? So maybe it's height and weight. And we measure one person, we measure their height, we measure their weight, we figure out where the corresponding spot is, and we put a dot there, right? That's called a scatter plot. And we're going to be using that in the next subsection. So the last one for this subsection is this graph, which demonstrates one of the most important things to know about whenever you make a graph. Is truncating the y-axis misleading? So if you just glance at this, it looks like it's half yes and half no. But if you look at the actual y-axis, the values that are being measured there, you'll see that the yes covers essentially 0 to 99, and no only covers the last 1%. But because the y-axis is truncated, and it's not showing 0 through 98, the kind of easily gathered information from just glancing at something is completely misleading. So when you make your graphs, make sure you're, having all of the possible values along the y-axis and the x-axis, so you can really show the kind of actual situation without exaggerating one side or the other by truncating off much of that, of the possible values for those variables. Anyway, we're going to go ahead and take a break. I'll be right back with a discussion on regression, which is one of my favorite statistical analysis techniques. Thank you very much. See you in just a minute.